Good morning, physicists. Today we are starting with the light part 3. This we will be starting with refraction of light. What is refraction? Whenever light enters from one medium to another which have different densities. Now here, densities does not mean the physical density. It means the optical density. Optical density, that means the restriction or obstruction or resistance offered by that medium to the light. As a result, the speed of light in that particular medium is affected. If the medium is optically denser, the speed of light will decrease. Otherwise, it will remain the same as in air, that is 3 into 10 to power 8 meters per second. The phenomenon of light, when it changes direction, whenever it enters from one medium to another which have different optical densities, is known as refraction of light. We can also say whenever light changes a medium, it bends, it changes its direction. That is called refraction, but that's a simpler definition. Now, within a medium, the light travels in a straight line. Here you can see that a pencil which is dipped in water. The portion which is dipped in water appears to be different from the portion that is in the air. This is due to refraction of light. There are certain terms related to refraction of light, just like reflection. There are some terms. Almost the same terms are there. The incident ray, the ray which is coming from one medium and it is about to enter in the second medium, that is the incident ray. The refracted ray is the ray which on entering the second medium, the change in direction. So that changed ray is called refracted ray. Angle of incidence. Now there is a boundary between the two media, that is, suppose we take glass and air, there is a boundary. On that boundary, where the incident ray strikes the second medium, we draw an imaginary line perpendicular to the boundary. That is known as normal. Just like we drew normal in case of reflection of light, here also we are drawing a normal. Now, the angle of incident ray with the normal is the angle of incidence, and the angle of refracted ray with the normal is the angle of refraction. And if the light is coming out from the second medium, that is known as angle of emergence. Refraction through a glass slab. The diagram is given in your textbooks. This is a glass slab. The AD, the line AD is the boundary between air and glass. O is the point of incidence where the incident light is striking the boundary. At O, we drew a normal perpendicular to AD. The incident light traveling from the air enters glass. Now, glass has a higher optical density than air. That means it will offer some resistance or some opposition to light. As a result, the speed of light decreases. And due to the decrease in the speed of light, the light ray which is traveling in the glass now has bent towards the normal. That means now light is not going along its original path, it's going along a changed path that is closer to the normal. Now from O to O dash, that is the second boundary where the glass plate has ended, and below it there is air again. So when the refracted ray strikes O dash, now it is entering into air from glass. Air has a less optical density than glass, therefore the ray of light will change its direction again. But now it will change its direction away from normal because the speed has gone back to its normal speed. In this particular case, there are two refractions. One when the light was entering from air to glass, and the other when the light was entering from glass to air. This is the entry point, this is the exit point. At entry, the light enters the glass from air, and as the glass has a higher optical density, the ray of light, that is the refracted light, will bend towards the normal. Inside the slab from O to O dash, the density of the glass is same throughout, therefore the light is traveling in a straight line. At the exit point, the light now is traveling from glass into the air. Here, as air is less optically dense than glass, therefore the ray of light that is emerging from glass will move away from normal. So this is the angle of emergence, angle of incidence, angle of refraction, and angle of emergence. Suppose this glass slab was not there. So what would have happened? The light would have traveled along its original path. Here the dotted line or the broken line shows the original direction, the original path of the light that the light was about to take. But due to the presence of this slab, the light has now shifted from its original path slightly, and the distance, the perpendicular distance between the original path and the emergent path is known as lateral displacement. This lateral displacement is directly proportional to the thickness of glass slab. If the glass slab is thinner, this displacement will be less, and if it is thicker, this displacement will be more. Just as we learnt in the reflection of light that there are laws that govern the reflection of light, similarly there are two laws that govern the refraction of light. The first is almost the same. The incident ray, the refracted ray, and the normal all lie in the same plane. Second law you have to learn because it's slightly different. It says that whenever refraction is occurring, the sign of angle of incidence and the sign of angle of refraction, they bear a constant ratio for a given pair of media. What do we mean by that? By that we mean that if we are taking two media, let's for example we take air and glass, then whatever be the angle of incidence and the corresponding angle of refraction, the ratio of sin I to sin R will be same for air and glass, whatever angle of incidence we take. This is constant for air and glass. This ratio, the constant, is also known as the refractive index of second medium with respect to first. Here the first medium being air and second medium being glass. So we will say that this is the refractive index of glass with respect to air. There's another method of calculating the refractive index. Suppose the light is traveling from air to glass, air being the first and glass being the second medium, then we will say that refractive index of second medium with respect to first, that this N21, this is interpreted as refractive index of second medium with respect to first, and in our example it will be the refractive index of glass with respect to air. It is the ratio of speed of glass in medium 1, that is air, divided by speed of glass in medium 2, that is speed of light in medium 2, that is glass. So speed of light in air divided by speed of light in glass will give the refractive index of what? Glass with respect to air. Some examples of refraction of light: the spectacles that people use to correct their vision, binoculars, cameras, telescopes, magnifying glass, all these are examples of refraction of light. Now, a prism, just as we discussed the case of refraction through a glass slab, now we will discuss the case of refraction through a prism. A prism is a triangular piece of glass with five faces actually, but because the diagram is two-dimensional, you will only see the first face, the front face. Here, the light is incident on the face AB obliquely like this. The red line represents the incident ray, E being the point of incidence. Now at E, we make a normal perpendicular to AB, that is EN. The light now will bend towards the normal. Why? Because light is entering from glass into air, therefore it will suffer a decrease in speed and will bend towards the normal. Now this is the refracted ray. Now at point F, the second refraction will take place, that is the exit point. At F again, we'll make a normal FM. Now at F, the light is entering from glass into the air. That means now it will have its speed increased, that is equal to 3 into 10 to the power 8 meters per second. So it will bend away from normal. So light went in this direction, suffered refraction, became straight, and when it emerged out of the prism at the other opposite face, it bent again. Now if we produce the incident ray up to a point H and we produce the emergent ray up to the point D, we see that EH is the origin direction of light and the emergent direction is FS. So the angle between the original direction and the emergent direction, the angle D, is known as angle of deviation. In the case of prism, the emergent light is not parallel to its incident light. Therefore, in this case, we will take angle D as the angle of deviation. That means the light, instead of traveling in its origin direction, has bent and suffered a change in its direction. The second diagram, this is known as dispersion of light. When the white light, after passing through a prism, is splitted into its component colors, the VIBGYOR, red being the topmost, violet being the downmost, this is known as spectrum. And this particular phenomena of splitting of white light into its component colors is known as dispersion of light. This and these, both the diagrams are important from exam point of view. Now coming to spherical lenses. Just as we study spherical mirrors, now these are spherical lenses. In spherical mirrors, the phenomenon was reflection, but in spherical lenses, the phenomenon will be refraction. This lens that is thin at the edges and thicker in the middle is known as convex lens or a converging lens. Why is it called converging? Because it is converging a parallel beam of light, so all the rays are meeting at a point. The beam of light which was traveling parallel now has converged to a point, therefore this is a converging lens. But if the same parallel beam of light is incident on a concave lens, we will notice that the rays are moving away from each other, that is, they are diverging away from each other, therefore it is a diverging lens. Here, the point at which all the rays seem to converge is called focus or the focal point. In case of concave lens, the divergent beam appears to emerge from a particular point That is also called a focal point, but that is on the opposite side. Here, the focus was on the right side, but in case of concave lens, the focus will be on the left side. Just like there was some sort of terminology in the case of spherical mirrors, almost the same terms are used in the case of spherical lenses also. The aperture, that means the diameter of the lens. If the lens is short, as in the case of binoculars, the aperture will be less, and if the lens is bigger, as in the case of magnifying glass, the aperture will be large. So aperture is small means lens is small, and aperture is big means lens is bigger. Optical center. Optical center plays the same role as the pole in case of mirrors. All the distance are measured from optical center, whether it's the distance of object, whether it's the distance of image, whether it's focus or radius of curvature, whatever, they are always measured from optical center. Then there is a radius of curvature. Spherical mirrors were a part of a big hollow sphere. Similarly, spherical lenses are also a part of the sphere, but that sphere is solid. But being a sphere, it would be having a center. That center is known as center of curvature, and the distance of center of curvature to the optical center of the lens is known as radius of curvature. The principal axis is the same. It joins the center of curvature to the optical center and is extended both ways infinitely. Principal axis. The focus, where the parallel beam of light seems to converge, or the divergent beam of light appears to emerge from the point, that is known as the focal point, and the distance of focal point from the optical center is known as the focal length of the lens. There was some sign convention in the case of spherical mirror. Similarly, almost the same methods, same rules apply to the lenses also. The sign convention in the case of spherical lenses. Concave lens, this one, and convex lens, this one. Optical center, both are having an optical center. Now this optical center plays the same role as the pole in case of mirror, and that is the point of origin in a graph. Distances measured towards right and up, they are taken positive, and distances measured towards left and down, they are taken as negative. Object will be placed on the left side, distance will be measured from the optical center towards the left side, therefore object distance again will be taken as negative, always. The object height, that is measured from the principal axis in the upward direction, therefore height of object always positive. The real image forms downwards, inverted, therefore it is measured downwards, therefore image size will be taken as negative for virtual image, for real image. And if the image is virtual, it will be erect, the image size of the virtual image will be positive. The focal length of convex lens is taken as positive, and the focal length of concave lens is taken as negative. Keep in mind that in the question, if the term comes out to be convex, whether it's a lens, whether it's a mirror, the f or focal length will be always positive. And if the term concave comes out, whether concave lens, whether concave mirror, the focal length will be negative. If you remember this, you will never attempt your numericals wrong. That concludes the third part of the series. Now in the fourth and concluding part, we will be discussing about the formation of image in the spherical lenses, combination of lenses, the power of lenses and their uses. Thank you.